Any expansion boards that fit in the PC must be compatible with an electrical interface standard called the 8-bit Industry Standard Architecture bus. Industry Standard Architecture is usually abbreviated ISA. Here's the basic set. It's a lot cheaper than $50. A straight slot screwdriver and a Phillips head screwdriver can do most any job in PCs or clones. The 34-wire cable carries control signals, and the other one, the 20-wire cable, carries the data. Now, both of those cables plug into the controller at this point. The controller has a 34-pin connection for the 34-wire cable and a 20-pin connection for the 20-wire cable. You will notice a place for a second 20-wire cable on your hard disk controller. That's because most hard disk controllers support 2 hard disks. Now, before you can put the drive itself into the system, you've got to adjust a couple of things. First, we adjust something called the terminator chip. You can see it over here on the Seagate 4096. Remember, I mentioned the 4096 before. Here it's turned upside down. You may not recognize it. It's right here. The terminator chip is right here. It may look like a normal chip, or perhaps, like in this case, like a very skinny chip. In any case, it's probably the only thing on your hard drive that looks like a chip in a socket. I'll show it to you here on the Seagate 225. Again, there it is. It's actually a resistor. The general rule with terminators is that the last drive on a cable keeps its terminator. If you've got other drives on that cable, you should remove their terminators. In the vast majority of cases, though, you'll only have one drive on the cable because you probably only have one hard disk. So leave the terminator on that drive. Next, we set this drive select jumper. It's a little tougher to see, but it's right over there. As you can have more than one drive on a cable, there's got to be some way to keep track of which drive is drive number 1 and which drive is drive number 2. That's what the drive select jumper does. We can come over and look at the drive select jumper on the 4096, and it's not far from the terminator, actually. Now, like most things in the computer world, we don't make it quite that simple. Some people wouldn't call them drives 1 and 2, but drives 0 and 1. The C drive is whichever is the first drive number. The D drive is whichever is the second drive number. Anyway, back to the jumpers. They may not be labeled, but it's pretty easy to figure out which is position 1. If we go back to the 4096, you can see that position 1 is usually on the outside. In the 4096's case, the jumper's on the outside, and that's position 1. You can see the same thing on the Seagate 225. There's all these jumper points, but this one's on the outside. It's in the first drive position. So we've seen the terminators and the jumpers on the 4096 and the 225. If there are no twists in your cable, then the jumpers work as you'd expect. Drive 1 is drive C, and drive 2 is drive D. On many systems, however, and real IBM systems in particular, you may see that your cable has a twist, like this one. You can see the twist here between wires 25 and 29. The twist reverses 1 and 2 as far as the controller is concerned. Say the controller's over here, and say the drive is here, and the twist is between them. If I jumper the drive to be drive 2, then it looks like drive 1 to the controller because of the twist. The twist reverses 1 and 2. If I jumper the drive to be drive 1, it looks like drive 2 to the controller, again because of the twist. On the other hand, if I put a drive on this non-twisted connector, then the controller sees it as whatever it's jumpered as. It partially summarizes what I've said here. In all cases, the last drive on the cable keeps the terminator, the other one loses it. Of the 4 cases in the book, 2 of them are pictured here on this graphic. In this graphic, there's no twist, so we jumper the drives accordingly. C is drive 1, D is drive 2. When there is a twist in the cable, as in this graphic, you end up setting both jumpers to the same position, as the twist makes the further drive reverse its jumper position. Now all we've got to do is put the drive in. AT-type systems, again we're going to put this in an AT, secure drives with rails on the side. That's this black plastic rail here. And then the drives can slide right in, like a drawer into a desk. XT systems work a little differently. XT-type systems generally screw the drive right into a support on the chassis. This brings up two simple rules you'll use in order to figure out what a board does. First, there's the what's it connected to rule. If the board's got a ribbon cable from it to the hard disk, well, chances are it's a hard disk controller. The second rule is the what kind of connector is on it rule. Female 25-hole socket, we'll see back here, is used for a Centronics parallel printer port. This board over here is the display controller board. I know this because it's connected, or it was connected, to the display before I took it off, and because of its connector type. This is a female 9-pin connector, the connector used for the first three kinds of video boards offered in the PC world. Those boards are the monochrome display adapter, the color graphics adapter, and the enhanced graphics adapter. Those names are a mouthful, so they're generally called the MDA, CGA, and EGA. We'll have to go over to the AT to look at the fourth type. The video graphics array, or VGA, uses this three-tiered connector. 3 rows of 5 holes offset from one another. Some have only 14 holes. That's 2 rows of 5 and 1 row of 4. Let's look quickly into the AT. And we'll see the power supply, the floppy drives, the hard drive, the combination hard disk and floppy disk controller, the VGA board itself, a memory expansion board, and a parallel and serial, I guess you could call this a multifunction board. Back in 1983, IBM offered a 10 megabyte hard disk subsystem for its new XT. As there weren't too many other hard disks around at the time, the hard disk controller was pretty much hardwired to only work with a 10 megabyte hard disk. A bit later, IBM offered a choice of hard disks, either 10 or 20 megabytes. To accommodate this, they used a controller from Xebec that could support either size. In fact, it could support 4 hard disks, 2 varieties of 10 meg, a variety of 20 meg, and a 5 megger. You indicate to the controller which drive you had by moving a jumper on the controller board. It was actually on the controller board. Soon, some vendors responded to the proliferation of hard disks and hard disk sizes by offering more and more jumper options. This practice is becoming less popular, however. The major vendors of XT hard disk controllers are instead using an auto-configure approach. In this approach, you configure your controller by running a program that puts the hard disk's vital statistics on a specific location on the hard disk. For example, commonly you'll see the first sector of the hard disk. That's referred to as cylinder 0, head 0, sector 1. Some AT-RLL controllers do the same thing. IBM wanted the AT to be flexible in handling hard disks, so they used yet another approach. They stored a table in the AT's BIOS ROM. The BIOS ROM chip's in the AT, recall. And this table had 14 popular hard disk types. Basically, IBM took the 14 most popular drive types and described them in the ROM. The user would then indicate which of the 14 types is closest to her hard disk with the AT setup program. 14 drive types, unfortunately, however, proved to be confining. So later, ATs had a table with 25 types. That wasn't enough either. So even later, ATs knew of 47 types. Most AT-type clones know of 47 or more drive types. Unfortunately, every clone has a slightly different drive table. What that means is, this drive, for example, that I referred to before, is a drive type 35 on one computer I've got. It's a drive type 44 on a different computer. That's because their ROM drive tables are different. You've got to have your computer's documentation to find out what your drive table is. Let's start with central processing units. They're the things I've mentioned a few times, called CPUs. Over here on the XT, here's the Intel 8088. It's the heart of the XT. Recall that I've mentioned one of the characteristics of the CPU is something called the CPU's megahertz. Megahertz is the speed of the clock circuit that drives the CPU. The clock is to a computer what a metronome is to a beginning piano player. It sets the pace for the system. There's another characteristic you need to know, the data path. The 8088 has an 8-bit data path. Now, 8-bit data path means that the doorway to the outside motherboard and expansion circuitry is only 8 bits wide. As the CPU can only read or write 8 bits of data at any instant in time, think of the data path then as the width of the CPU's front door, the most data that can be transported in or out at any point in time. In the case, again, of the 8088, the data path is, again, 8 bits, and the typical clock rate is from 4.77 to 10 megahertz. Now let's go over to the AT motherboard. Here's the 8286 on the AT motherboard. It runs at 8 megahertz. The data path on the 286 is 16 bits, twice as wide as the 8088. Moving over to the 386 motherboard, the processor on the 386 motherboard is the 386DX chip. Now, if you take a close look here at the lettering on top of this chip, then you'll be able to see that it says 8386DX-20. The -20 means that this particular 386 can operate at up to 20 megahertz. The 386DX has a 32-bit data path, even larger than the 286. This board in the back has this odd connector on the back called a DB25 connector. There's actually two of them here. It's called that because it kind of looks like a capital D from the side, and there are 25 tiny pins. You'll see two kinds of them on a PC. One with 25 pins, that's the male connector, and one with 25 holes, that's the female connector. The male plug is used for the serial or RS-232 port, again used to connect modems and sometimes printers. I'll go back to the XT and remove the floppy disk controller. Now, because it's got a cable on it, we've got to be a little more careful. First, I remove the ribbon that connects it to the floppy disk drive. There's the controller, there's the floppy, and there's the ribbon. I'm going to be careful. Now, before you move this away, make a note in your notebook how it goes back on. Now, in this case, it's easy. There's a key. But even if there weren't, there's a little trick that makes connecting ribbon cables easy. Notice that one of the wires on the edge of the cable is colored differently from the ones around it. It's a blue against a gray ribbon. This is wire number 1, and it should connect to edge pin number 1. Let me take the board out and you'll see it a little better. Being very careful not to nick these cables. It's quite easy to do. Look at an edge connector like this one. Over here, can you see the 2? That's the silver 2, not the big white P2. Now down this way, you don't have to see that far, but down this way there's a 34. You may be able to see that also. Let's go back to the 2. Now, pin 1 goes right next to the 2. So when you're reconnecting the cable, make sure the blue line goes to the side where the 2 is. Now, if we look closely at this board, I've got to turn it upside down, or turn it around, so that you can see these numbers right side up. The only thing really interesting on this board is this chip, It's the large chip, the NEC 765 disk controller chip. You may instead have, and in this case we do have, the Intel version, which is the Intel 8272. Some technical manuals just call it the NEC chip. If a floppy controller dies on you, you could try to change this chip, but more likely, just buy a new floppy controller. Now I'll remove the hard disk controller board. As it's got a bunch of cables on it, it's usually easier to remove the mounting bracket first, the mounting screw, rather. Then remove the board a bit and disconnect the cables. Take these two cables off. Note there's two cables, a 34-wire cable and a 20-wire cable. There may be a second 20-wire cable here. Twist it around so you can see it. There may be a second 20-wire cable here, but there isn't in this case, but it's not used. Remember to note how they connect, although they'll probably follow the pin 1 rule. Matter of fact, I learned the pin 1 rule while installing a hard disk. I got a box with a controller, a drive, and two cables. It was easy to see where the 20 and 34-wire cables went, but each cable could go one way or another. So I figured, what the heck, I got a 50-50 chance, and plugged in the cables one way, the wrong way as it turned out. I left the room to get a soda while I was waiting for the PC to boot up, and when I returned, I smelled that awful burning smell. So I later asked around, and that's when I found out the pin 1 rule. Take a little closer look here. Notice there are connectors for two 20-pin cables and one 34-pin cable. If we come in real close here, you can even see the 2. See, there's a 2. And there's a 1 even on the other side of it. So once again, our pin 1 rule works out. Now these two 20-pin connectors allow this to accommodate two hard disks. Each disk has its own 20-pin connector, and the 34-pin connector is daisy chain. The 34-pin connector is up here. It has two connectors on one end. It generally doesn't matter which 20-pin connector you use when connecting the first hard drive. Let's go over a bit and take a look at the ROM on the board. Notice we have a couple of ROM chips here, and on this one I can even read, I'll turn it around so you can read it, I can even read a version number. What is that? 1048333A. I have no idea what that means, but I'd write that down in my notebook. Then we move all the way to the end of the board where we see option. Note the jumpers or the dip switches. In this case we've got jumpers, some have dip switches. Controllers, XT controllers at least, are usually made to support a wide variety of disk types. You tell the controller what type to expect by setting the jumpers or the dip switches. How do you know how to set them? Well, you'll find the exact setting in the manual that came with the controller. If your controller didn't come with a manual, contact the manufacturer and get one. You'll find manuals on all of your boards. Come in handy at some point. Remove the power connection here. Notice this is a milky white connector with 4 wires in it. And it's best if you can grasp it on the connector body, but I find if you grab all 4 wires and wiggle it back and forth like that, it'll come off for you. Note the hard disk and the floppy disks use similar looking power connections, and they are in fact identical, and it doesn't matter which is connected to which. Some people think that one connector's for the hard disk and one's for the floppy. That's not true. Over on the AT, I've already pulled the power connector, but you may see this over here, this black wire? That's a grounding wire, and you just pull it off. Then remove the data connections. There's one here on the AT, and one over here on the XT. If you can see that, notice again the marking for pin 2 and pin 34. Let me pull a, yeah, you can see it. It's good. See that too. Take my drive out,
And please, when you're taking drives out, be careful about these little components that are standing up on top of the drive. As you pull them out, if you're not careful, you can behead these little components. Back over to the AT, and then we'll finally get this AT floppy out. The floppy cable, once it's removed, looks like this. This side goes to the controller, and these connectors go to A and B. But how do I know which is A and which is B? Well, I hope you made a note in your notebook before taking it apart. Notice the end of the cable has a twist in it. This looks like it's been cut, but what actually happened is they cut it, they twist it, and they put it back together. The twist is right there. This is the end that goes in A. The twist tells the controller which drive is A. Keep an extra cable around just to test other cables with. Let's look at the drive. If we look at the XT drive here. First, notice this thing that looks like a socketed chip. It isn't. It's a resistor called a terminating resistor or a terminator. Most drives come with a terminator. I can show you a similar one on the AT. Again, if we look at an AT floppy disk, once again, the only thing that looks like a chip in a socket, that's our terminator. The A drive must have a terminator. Remove it from the B drive. Maintaining drives is simple. Don't put any diskettes in the drives that are obviously dirty or wet. Avoid really cheap diskettes. The oxide on them can flake off and damage the drive heads. If a problem arises, use a head cleaner kit to clean the disk heads. And if the problem persists, should you try to adjust the alignment of the drive? I would say not. It requires expensive tools and is time consuming. The drives are cheap, usually under $90 and as little as $50 in some cases. Just keep a few on hand and replace the bad ones. Oh, and here's a little protection tip. When you're not using the drives or are moving the drives, don't close the drive doors. Leave them open. You see, there are two drive heads. One to read and write the top of a floppy and one to read and write the bottom of a floppy. They're like this when the door's open. If you close the door with no floppy in the drive, the two heads bash against each other. You can damage both heads that way. When you have a disk problem, first check the diskette. Then clean the heads on the disk drive. Try swapping the drive after that, and if you're still not having any luck, swap the controller and the cable. And don't forget that sometimes a simple reboot can reset the drive system, solving the problem.
There are 3 steps to hard disk software installation. Even if you've worked with hard disks before, you may not have done all 3 in the past, as your dealer may have handled the first step. That first step is the low-level format. The low-level format sets up the areas on the hard disk that the system will use later to distinguish one sector from another. In this picture, you see an unformatted disk. It's just tracks. There are no sector delineations. Think of an unformatted disk as being like a new road. You've got to paint the lines on the road and put up road signs. That's what low-level format does. In this picture, you see the effect of low-level format. Sector IDs are written on the disk, separating the sectors. Low-level formatting also destroys all data on your hard disk, so don't experiment on a disk with important data unless there's a backup. Some controllers require their own special low-level format program. It's actually stored on a chip on the controller. Such a chip is called a ROM, or read-only memory. The debug program that came with your DOS can activate such a program if it exists. Brand of drive and controller have special characteristics that separate them from other drives and controllers. We'll look at these characteristics first. Think of it this way. If you were going to buy or service a car, you'd have to know things like how many cylinders the engine has, whether or not it's got automatic transmission, and what kind of oil it takes, right? Just like that car, a hard disk has a few vital statistics that describe it. So let's see what they are and what they mean. Hard disks have several characteristics: number of heads, number of cylinders, number of sectors per cylinder, seek time, write precompensation cylinder, reduced write cylinder, head step rate, drive to controller interface. Let's take a closer look at some of these characteristics. Heads, cylinders, and sectors tell you how large a hard disk is. Seek time tells you how quickly the disk can retrieve data. Actually, that's only half the speed equation. Your disk is also affected by its interleave factor, but we'll see that later. That intimidating-looking trio near the end are mainly used when performing an operation called low-level formatting on a disk. That's part of preparing a disk for use, and we'll get to that later on in the program. The interface is the language that the hard disk and the drive use to communicate. Here's a drive with the cover off. Please don't do this to your drive. This drive was dead before I got it. How does a disk store data? Notice first that there's more than one platter. Two, in fact. We use both sides of each platter, so there's 4 surfaces to store data on. The data is stored magnetically, as is done with a video cassette. Some hard disks use as little as 2 surfaces, some use as many as 16. Note here that there is a read-write head for each surface. So some people would call this a 4-surface disk. Some would call it a 4-head disk. You'll see both terms interchangeably. Each surface is then divided into cylinders or tracks. Cylinder and track are 2 more terms that are pretty much used interchangeably, although there is a difference in meaning, although not one we'll worry about. Each surface of this 5¼ inch disk is divided up into 615 concentric tracks. Imagine 615 tracks in this small space. And these drives only use about a 1-inch wide band to actually store the data. Imagine 615 tracks in that small space means each track is just a little bit wider than 1/1000th of an inch. Kind of makes it easy to understand why hard drives are so fragile. Some drives only put about 300 tracks in this space. Others put over 2,000 cylinders in that small band. By the way, the first cylinder is numbered not 1, but 0. Computer people often do that, counting from 0. Ask a techie to count his fingers, and he'll count 0, 1, 2, 3, 4. The tracks are then cut up like wedges of pie into sectors. Most drives divide a track into 17 sectors, although some others, as I'll explain later, attempt to squeeze more data on the disk by putting more sectors on each track. Finally, each sector contains 512 bytes. 512 is also 1/2 of a K, and that's easier to compute with, so I'll generally just refer to it as 1/2 K. Let's summarize. We have 4 surfaces times 615 tracks per surface times 17 sectors per track times 1/2 K bytes per sector, which gives just under 21 megabytes.
Hard disk and hard disk controller do the same kind of thing as the floppy drive and controller, but the hard disk, of course, can hold more data and access it more quickly. Note that the hard disk controller communicates with the hard disk drive via 2 cables. That's if you've got the kind of disk called an ST506 or ESDI drive, or 1 cable if you've got the kinds called SCSI or IDE drives. The controller plugs into the system board, and the drive is mounted in the chassis.
The PC world first heard about a hard disk notion called interleave factor way back in 1985. It always surprises me that this is still an issue in the PC business, but hardly a month goes by that I don't see some poor user wasting time with a misinterleaved disk. The sad part is, it shouldn't cost him more than a dime to fix this. Recall that each track on most hard disks is divided up into 17 sectors. We'll use MFM for the example here. Each sector holds a mere 1/2 K bytes, not a lot of space. As a result, when we need 1 sector on a disk, we usually end up needing all 17 sectors. So we need to arrange these sectors so they can be read in order in the smallest number of rotations on the disk. Now it seems that this arrangement is the fastest, so all 17 sectors get sucked up on the first pass. Unfortunately, it's usually not that easy. By the way, this is called a one-to-one interleave, as each sector is just one sector away from the next one in order. To see why this won't work, let's look at a few milliseconds in the life of a hard disk. Imagine that this disk is looking to read sector 1. A disk head, like the hand of a clock, appears in this graphic around sector 15. It will move clockwise. The disk head senses the data that sweeps under it as it waits for sector 1. The data is moving by pretty quickly at 60 revolutions per second. Sector 1 appears under the head, and the disk starts reading the data in sector 1 as it goes by. You'd think that by now, sector 1 has been read, the controller would tell the drive to start reading sector 2, but it doesn't. You see, the controller still has some work to do. One of the controller's functions is data integrity. It's got to calculate the ECC, the error correction code, remember? That takes time. While the controller is calculating, the disk keeps spinning. So when the controller is ready for sector 2, it's missed it. And it has to wait an entire rotation for its return. That means we only get one sector per rotation, which is a pretty lousy data transfer rate. A better approach would be to stagger the sectors. This is called the 1 to 3 interleave disk you're looking at now. It's called that because if you start from sector 1 and move clockwise, 1, 2, 3 sectors, you'll get to sector 2. Count 3 more from 2, and you get to 3. 3 more and you get to 4, 3 more to 5, and so on. Now let's try our sector reads. The disk reads sector 1, and the controller starts calculating. Now, by the time the controller has finished its error correction calculation, the head is still short of sector 2, and we're positioned perfectly to read sector 2 next. You see, how fast the controller calculates determines how best to interleave the disk.
This is an older XT slot, and this is the AT slot. It looks like an XT slot, but it's a bit longer. It supports 16 bits of data transfer. Even though this slot was introduced in 1984, it's still the most common bus in the desktop PC market and is now known as ISA, the industry standard architecture. Here's a 16-bit ISA board. If we compare it to an 8-bit ISA board, you see that there's an extra connector. Remember that the 16-bit capability of the 286 prompted the creation of the 16-bit ISA bus. Well, now CPU chips continue to improve, and so the 386DX, 486, and later chips have a 32-bit data transfer capability, a 32-bit data path. That's a motivation for the Extended Industry Standard Architecture, or ESA, bus. It supports a 32-bit data transfer capability. ESA is not as common as ISA, but it carves out a greater share of the PC market each year. They don't look a lot different, but let's look at one anyway. Down here in this ESA machine, that's what an ESA slot looks like. Note that it looks very much like an ISA slot, but it's higher. That's because ESA slots are double-decker slots. The top part of each connector supports ISA for backward compatibility, and the bottom supports ESA. To see that, let's compare two boards. Here's the 16-bit ISA you've already seen, and here's an ESA board. You can see the ESA board projects further than the ISA board. We talked about 8-bit boards before. As you'd expect, 8-bit boards work in either 16-bit ISA, 8-bit ISA, or ESA slots. 16-bit ISA boards work in either 16-bit ISA slots or ESA slots. And ESA boards only work in ESA slots. But what about this? Can I take a 16-bit ISA board and put it in an 8-bit ISA slot? Well, ordinarily the answer is no. But some 16-bit boards are so-called smart sensing boards. These are boards that sense whether they're in an 8 or 16-bit slot. You plug them in and they kind of go, figure out what sort of slot they're in and behave accordingly. Some VGA boards and LAN boards come to mind here. And by the way, here's a surprising fact about these buses. No matter how fast your computer is, its bus generally won't run faster than 8 or 10 megahertz. That means a 50 megahertz computer runs only at 8 megahertz when communicating with something in a bus slot, something like a video board, a hard disk controller, or whatever. Now, in general, that's not a terrible thing. I mean, you needn't talk to your printer or your floppy drive or your mouse at 8 megahertz. Neither one runs anywhere near that speed. But that means that putting memory on an add-in expansion board is not a very good idea, at least not on a computer faster than 10 megahertz. Whenever accessing memory in an expansion slot, the PC slows down to the slower bus speed, slowing your 50 megahertz number cruncher down to 8 megahertz. That's why, when buying a PC, you should look closely at how much memory you can put on the motherboard. It's surprising how little memory motherboards from some big names can accommodate. Look for the ability to put at least 16 megabytes on the motherboard, even if you're not going to use it immediately. Believe me, you'll get there eventually. Now, of course, there's an exception to that rule about slow buses. Some vendors like Compaq, or for that matter, this no-name 386 clone, have built quite a number of fast PCs that are equipped with one special high-speed slot designed specifically for memory. You can see it here. You'll know you've got one if you have a board with an unusual connector. That's that board over here. Notice the edge connector's in a funny spot, like this board. Now, that's an important thing to know if you're buying one of these computers. Now, it's also not unusual to see a motherboard today that has room for 8 megabytes of memory, but that expands to 16. That computer will probably expand to 16 megabytes with the addition of the special board that goes into that special high-speed slot. Now, with some computers, all the memory goes on that board. With others, the extra 8 megabytes or more goes on that expansion board. Here's the catch, though. That special board is only available from that PC's vendor. For example, the special board for Compaq machines won't work in the same slot as the special board for Everex machines, which won't work in the same slot as the special board for ASTs, and so on. Many people see that their computer will take 8 megabytes on the motherboard and say, 8 megs, that's a lot. No point in buying the expansion board for the second 8 megabytes yet, because I can always wait. I'll wait till I need more than 8 megabytes, and then I'll buy the memory expansion board. The trouble is, once you need the special board, the PC maker will have gone on to more advanced computers, or they may have gone out of business altogether. They won't be selling your special expansion board anymore, and so you're stuck. Now, that special expansion board generally only costs around $100, so buy it when you buy the PC, even if you're not going to use it immediately. Looking over at the 386 motherboard, here's where a math coprocessor goes on the 386 motherboard. The math coprocessor for the 386 is, can you guess it, a 387. Note that it is in a square pin grid array package, just like the processor. A field of products called multifunction cards sprang up to fill in some user needs and to save slots. Now and then, truly amazing multifunction boards pop up, ones that incorporate local area network connections, hard disk controllers, and the like. It's really only limited by the imagination and ingenuity of the board's designers. Multifunction boards plug onto the system board. Every PC is composed of a few major parts. The principal parts of a PC are the chassis, the system board, the display board and the display, the floppy disk controller and floppy disk drives, the hard disk controller and hard disk drives, the multifunction card, the keyboard, and the power supply. The PS2s departed from the traditional PC architecture in that they used heavily integrated motherboards. This means that rather than having separate circuit boards to handle the functions of the video, hard and floppy disk controllers and the like, the PS2s pack most electronic functions onto the motherboard. The PS2 models use a completely different type of bus expansion slot from ISA. These slots are called micro-channel architecture, or MCA. Expansion boards for 8-bit or 16-bit ISA computers, you've seen this before, will not work in PS2 computers. The power supply converts line current to direct current used by the PC. In general, you won't fix the power supply. You'll just replace it. Power supplies are rated in watts. The higher the wattage, the greater the capacity, and in general, the larger the fan. A larger capacity power supply means your PC runs cooler and lives longer, so don't just purchase the minimum. Other color monitors are one kind or another of a class of display devices called RGB monitors. Here's CGA, EGA, and VGA. Those monitors are all types of RGB monitor. RGB monitors use a digital signal like the monochrome TTL monitor does. But now there are separate digital signals for red, green, and blue, hence the name RGB. Remove this screw holding in the mounting bracket to the back of the board. Generally, this is a 3/16-inch hex head screw. Take that out, and of course put it in my cup. Then I grasp the board in the front and the back and rock the board up and out, and then put it aside. If you have anti-static foam, that's nice to put it on. In my experience, it doesn't matter much. However, what does matter is how you handle the board. You can handle a board like this, you can handle a board like this, you can handle a board like this, but don't handle it like this. Keep your fingers away from the gold edge connectors on the board. You don't even see it, but your fingers have a layer of gunk on them that can impede a board's working properly. And by the way, it doesn't matter which of these expansion slots you put the board back in. In 99% of the cases, there's no difference between one slot and another. ROM is, again, read-only memory, a memory chip that has had data essentially burned into it. It doesn't lose data when turned off, unlike RAM. I don't know if I've made that clear, but when you turn a computer off, any information in RAM is lost. Techies would say that RAM is volatile. ROM, because it does not forget when you turn it off, is called non-volatile. We've seen some ROMs on add-in boards. Well, let's look on the motherboards and let's find the most important ROM. That's your system ROMs, the ones that contain the system's BIOS. If we look over here on the XT motherboard, oh, by the way, BIOS is Basic Input-Output System. It's a set of software routines that are absolutely essential for making your computer work. True blue IBM computers have ROMs containing a BIOS written by IBM programmers. That's why if you could see it closer, you don't have to, but if you could see it closer, you'd see a copyright IBM on here. You can't copyright hardware. What they're copyrighting is the software inside. Now, as compatibles cannot copy IBM's BIOS, there are three companies that specialize in creating BIOSes that legally copy the functionality of IBM's BIOS without copying the BIOS itself. You may have heard of them: Phoenix, Award, and AMI, which is American Megatrends Incorporated. A better written BIOS means a more compatible computer. So we've seen the XT's BIOS ROM. Let's go over now to the AT. The AT over here has a couple of ROMs. BIOS ROM on the AT motherboard. And next to them you can even see room for some more ROMs. Very few applications have actually made use of this, but it does exist. Those are both IBM. If we go over to the clone, the 386 clone, notice he's got a couple of ROMs there. See the attractive labels. So in the 386 clone, you see the BIOS ROM here. This is the parallel serial card. Let me just turn it just a little bit so you can read those numbers. If we look at the connectors, it's a male 9 connector, and a male 9 connector, you may recall, is a serial port. Female 25 is a parallel port. A SIM is a small circuit board that has memory chips mounted right on it. It's mounted right on it, and I can't remove these chips. You see 6 here, but you may see 3, or you may see 9. It depends on how it's arranged. Its small edge connector plugs into a special socket on the motherboard of a properly equipped memory expansion board. It generally does the job of 9 chips, so one SIM would equal 1 bank of memory on our 8088 computer. Small screwdrivers are useful for working with small screws, like the kind that secure connectors into the back of PCs. They can also help extracting chips from sockets, like so. The VGA is probably the last IBM video standard that will ever see catch on in the market. There's been later ones, 8514, XGA, and others. But the VGA is the last that's caught on as a standard. For a few years now, the market has been split with so-called super VGA boards. This is a super VGA board. Actually, it's not a vanilla VGA board. Video coprocessors and the current IBM offerings. So let's take a look at a basic VGA board. Notice the group of nicely spaced identical chips and room for more of them. We'll see later that this is memory. Most folks don't know this, but there's memory on every video board. 256K, in fact, with this guy, and more on more advanced boards. By the way, that video RAM, as the memory is called, does not count towards your system's total memory. A 640K system with a VGA actually has 640K of user memory plus 256K of video memory. What's the video memory do? Well, it holds the current system image. That image is constantly scanned by the VGA chip here, as the video board must send 60 or more screens full of signal to the monitor in each second. That data is output in a digital fashion, and then this chip, the DAC, or digital to analog converter, produces the analog signal that the VGA chip requires. Then the signal exits the board out here, the 15-pin VGA connector. Some VGAs have this 9 also. You'll notice this one does. And before I leave this, I should mention that, once again, we've got ROMs right here. I don't know if you can see that, but this, I see that it says V3-1.05. That's a version number.